Okay, this is 2023 Mechanics, Set 2, Question 2. A student conducts an investigation to determine the relationship between the period of oscillation of a system of the motion detector. The student releases it from rest and records the period of oscillation for the system consisting of this single spring and block. Now we attach an identical spring to the block and we do the same procedure and we release it, and we do this from 2 all the way up to 10 springs. Now, when this first question comes along, it says derive an expression for the period as a function of n. Express your answers in terms of m, k, n, and physical constants as appropriate. We're going to brute force this one because this makes the most sense, I think. 2 pi times the square root of m. Okay, excuse me. 2 ways you can look at this one. You can look at this one in that these have, if you consider this to be like one spring, if you look at it as a system, the k total is going to be 2k because you have 2 springs. Okay, so your period here would be 2 pi times the square root of m over 2k. Okay, that's a very, very quick route to get there, and you see that. But if you brute force it, and if you're not sure about a spring in series or parallel, what's going to happen, I want you to think about it like 2 people are holding something up. So you got 2 springs holding this up. So each spring has to hold half, right? So each spring holds m over 2. Not all of it, they hold half of it. So in that case, the period of each spring is going to be 2 pi times the square root of what they're holding up, which is m over 2, over their spring constant, k. And what do you get? You get 2 pi times the square root of m over 2k. Oh my gosh, we end up with the same period that time. Well, what if I have 3 springs? What are they going to be? Well, they're going to be a total of 3k. So it's going to be this over 3k. If I have 4 springs, 4k. Because what are they going to do? They're going to hold up a fourth of the block. So how many ever springs I put, that goes down here on the bottom. So the period for these is going to be 2 pi times the square root of m over nk. How many ever I have, that's going to be multiplied by k to get my effective spring constant of that system. All right. Next part. I stapled these together. On the following axes, sketch a graph of t as a function of n for n's greater than or equal to 1. So t is equal to 2 pi times the square root of m over nk. All right, and so the slope of this line would be t over n, but that's not what, we don't have a linear graph, so that's not going to matter. But another way I can look at it is this is my x, this is my y. So period is equal to 2 pi times the square root of m over k times the square root of 1 over n. Now the reason that I did that is because this is a constant. Like this is just going to be some number, okay, maybe 3 or whatever. But this is not. This is going to change as we go along, you know, whatever is going to happen. And so if I plug in values, so let's say, let's pretend, okay, I'm going to pretend this first number is 2. So 2 times 1 over n, or 2 over the square root of n. Okay, I'm just going to make up a number and use it as 2, because this is just a shape. That's all I need is a shape. I don't need anything spectacular. I just need a, what does this look like? Now, if you know what that function is going to look like as far as shapes, good job. But if you don't and you need a little help, you can always put in your x and your y, which is your n and your t, because that's what we got going on in this graph. That's what they labeled them as. So it's going to be everything greater than 1. So let's just put 1, 2, 3, 4 in here. Let's see what happens. If I put in 1, I get 2 over 1, which is 2. If I put in 2 over the square root of 2, I get 2 divided by the square root of 2 is 1.4. I get 2 divided by the square root of 3. This is 1.41. This is 1.15. 2 over the square root of 4. Square root of 4 is 2. So that gives me 1. If I want to go a little farther, I could put a 5 in there. 2 over square root of 5. This is not terribly time consuming. You could also put this into your graphing calculator because you will have that on the test. And so you get 0.89. But I can see what's happening. I decreased by 0.6. I decreased by 0.25. I decreased by 0.15. I decreased by 0.10-ish. Now these are estimates. Okay, I understand that that's not exactly 10. But you can see that I dropped a lot. My period is big at the beginning. And then I drop down, down, down. Where am I going to go to if I get down here and my n is infinity? Well, if I put infinity over there, I'm going to get 2 over infinity, and I'm going to be asymptotic to 0. So I know this is going to have an asymptote. So I'm going to start big, and then I'm going to head down here to 0. Well, it's got to start like here. There wouldn't be this part. Like this would be n equals 1 right there. And then we'd start going that way. I mean, I guess you could go ahead and extend that because it's going to go asymptotic to that way. So that's our shape that we have. Because if you put 2 over 0, we're going to approach infinity there. All right, some of my favorite things that they ever ask us to do is stuff like this. Probably only worth 1 point, but they say, okay, so here's the data for t squared as a function of n to the negative 1 as shown. Draw a best fit line for the data. So here I go with my handy dandy ruler. I'm going to draw that. I drew a best fit line. I'm probably going to need to find the what? The slope, right? Okay, so let's see what we've got to do with it. The mass of the block is measured to be 1.5. Using the graph, calculate an experimental value for K. Okay, this is where if you didn't know what you were doing before, make something up because you're going to use it. So I'm going to go back to this part right here. 2 pi. So my period is 2 pi times the square root of m over nk. All right, now I want an experimental value for k, so I'm going to solve for k. So t over 2 pi is equal to the square root of m over nk. I'm going to square both sides such that I get t squared over 4 pi squared is equal to m over nk. Now I'm going to do a little moving, okay? I'm going to multiply both sides by k. I'll do this step by step so you can see what I'm doing. So k times t squared over 4 pi squared is equal to m over n. All right, then I'm going to flip this, multiply by the reciprocal, so we'll just do this, and I'll write 4 pi squared over t squared, multiplied throughout, so over here I get k, and over here I get 4 pi squared m times 1 over nt squared. Now, you might be wondering, that's kind of weird, why'd she do that? Well, because I know that n and t squared are in my graph, so I bet they're going to have something to do with the slope, and this is a constant because this is 4 pi squared times 1.5. So we need to figure out how that's related. Well, my slope up here is going to be my rise, which is t squared, over my run, which is n to the negative 1. Well, when you divide by something to the negative 1, that's like t squared over 1 over n, so that's going to be t squared times n. So t squared times n is my slope. Hey, t squared times n is my slope. So 1 over the slope of my line. So now I know that I need to find, that's what my k value is. So I need to find my slope. So 4 pi squared times 1.5 times 1 over my slope. So let's pick some points here. Ooh, that's a good intersection. Okay, I'm looking for things that are not data points. That's a good intersection. Yours may be a little bit different than mine. But let's find that slope. We're going to do our y coordinate here, which is 7, minus our y coordinate here, which is 3.5, all over my x coordinate of 0.6, minus my x coordinate of 0.3. So I end up with 3.5 over 0.3 for a total of 11.7. Okay? Now, this is 11.7 seconds squared because my slope, my rise is t squared. This is just a number. Okay, so that's what I'm going to end up getting. And then this is 11.7. 11. Okay, make sure that looks like 11, it's not 1.7, it's 11.7. Okay, so I'm going to calculate the value of that. So 4 pi squared times 1.5 divided by 11.7. And that gives me a K of 5.1 newtons per meter. Now, if you're wondering, well, how in the world did she get newtons per meter? This is a kilogram. A newton is a kilogram meter per second squared. A newton per meter would be a kilogram over a second squared. This is kilograms. This is second squared. So that's what we have. Spring constants are always measured in newtons per meter anyway. So it's just a kind of a common, like a knowledge thing that I have going on there, but then you can go back and find those units if you've forgotten it. All right, now in 3, I think this is the last part of this question, maybe. Is there another one? No, there's more. Okay. The student finds that the value given by the manufacturer for the spring constant is larger than what they found it to be, and they want to know a single source of experimental error that could result in the observed difference. So we want a larger K. Okay, well, a larger K, if this stuff is constant, okay, if that I didn't measure wrong, okay, then the slope could change. So larger K means a smaller slope. Okay, my slope is t squared times n. Now I'm probably not going to miscount the number of springs that I have attached, right? So what am I going to be able to measure wrong? The period. So perhaps the students measured the period incorrectly. Okay, how would they measure it incorrectly? Well, if my slope is smaller, that means my t is smaller. And so maybe they didn't start recording at the right place, at the right time. Okay, maybe a little bit of lag happened and they didn't start recording. Maybe they didn't move their hand away or something happened that it didn't just take off. They got the wrong period. Okay, letter D. Okay, the student says, okay, I'm going to do a similar investigation and I'm going to do it with a number of springs again, but this time I'm going to do it horizontally on a table. There's no friction, it's negligible, and in each trial it's displaced the same horizontal distance, and they plot period as a function of n to the negative 1 for this new data. Would the slope of the best fit line from this new investigation be greater than, less than, or the same as the slope from before? Well, our slope was nt squared. Again, n is not going to change. Like we're going to know, I've got 1 spring, I've got 2 springs, I've got 3 springs. That's going to stay pretty easily measured. But let's look at t. So period is 2 pi times the square root of m over 2k. That's still the period because I'm not changing the mass and I'm not changing the springs, so the spring constant is staying the same. That's supposed to be nk, not 2. My bad. Nk. Okay, the spring constant is going to stay the same because it's the same springs. And if n stays the same, then all of this stays the same. So the period stays the same, n stays the same, so the slope stays the same. And there's our justification for that. All right, and lastly, when n equals 1, the maximum speed is found to be Vmax. If we put more n's on it, what's our velocity going to do? And you can really just kind of think this one through, but the more springs you have, the more it's pulling, and so therefore the quicker it gets it back to the beginning, to the middle. So we have a shorter period because we don't go as far, but we go faster. So if you've ever oscillated, if you put a mass on a spring, if you put okay, let's Let's look at this. Let's say period is 2 pi times the square root of m over 2k. All right, if I put a big mass on there and I oscillate it, this is what I usually show my students. I put a little mass, it goes really fast. If I put a big mass, then it takes a lot longer to do, because the bigger the mass, the longer the period, so it's slower. Well, we're not changing the mass, we're changing the spring constant, because, oh, I did it again, I put 2 down there. Why do I keep doing that? So it's nk. This number right here, as I increase my n, I'm increasing this bottom number, which is going to decrease my period. And because of that decreasing period, my velocity, remember my angular velocity is 2 pi over the period. And so that's like how fast I repeat myself. And as I go through that middle, this is going to increase that angular velocity. I'm going to repeat that motion quicker. So my velocity is going to increase. And that's because the period is shorter. Then this is angular frequency. That's what I meant to say. Then angular frequency increases, and therefore Vmax increases. Because you could even go to simple harmonic motion with this, and you could say that velocity is negative omega xm sine of omega t plus v. But when you're maxing out, that's 1, right? And so when that's 1, then Vmax is going to be negative omega times your x max. Well, if my omega gets bigger, then my Vmax is going to get bigger. Okay, that's probably a better justification to throw the simple harmonic motion stuff at it.